arcs, two semicircular arcs, where one arc has a bigger radius than the other, but they share the same center of curvature. So here's our arc, kind of looks like a little rainbow. Here's our center of curvature, and the current flows through this loop in the following direction. So down on that side, up and around, back over this way. And we are asked to figure out the magnitude and direction at that center of curvature. So there's our point of interest. We have that the current is just under an amp, 0.77 amps. We have that the outer radius, which we'll call R2, is 11.6 centimeters. So we're going to calculate a numerical value here. And the inner radius is 4.5 centimeters. All right, so let's label these things. And I called this one 1, 2, 3, and 4. And so the first thing to take a look at is, what does DL crossed into R hat look like at each of these, right? And remember, the magnitude of this is going to be the magnitude of DL, which is going to be some combination of dx and dy in this case, times the magnitude of R hat, which is always equal to 1, times the sine of the angle between those two. Now, DL for 2 is pointing from left to right, and R hat here to our point of interest would also be pointing in the same direction. And so for 2, these things are parallel. And for 4, well, we would still have DL pointing from left to right, but R hat would be pointing in exactly the opposite direction, so we can call this anti-parallel. Either way, you get the sine of 0 or the sine of 180, and that is a 0. And so DL cross R hat for 2 and 4 is going to be 0. 0 for segment 2 and 4. And so we are going to effectively ignore the contribution from those two segments because there is none. Okay, so for 1 and 2, for 1 and 3, let's look at the direction of this thing first. So DL crossed into R hat. Now for this, I would encourage you to use the technique of pretending to grab the current, where your thumb is in the same direction of the current and you wrap your fingers through. And so if you do that for segment 1, our thumbs are pointing to the left, and so our fingers are coming out at us. And so the direction down at our point of interest is going to be out of the page. For 3, it's going to be the opposite. And when we combine these two, we're essentially going to pick one as positive and one as negative, and we'll talk about that in a second. But now our thumbs are pointing to the right, and now as I curl my fingers around that loop, around that bar there of current, they point back into the page when they intersect C. So you can imagine it kind of, your fingers getting really, really long, wrapping all the way around, and they would be going into the page when you do that. Now, what about the magnitude of this, of DL crossed into R hat? Well, the magnitude for segment 1, DL, the magnitude of DL, more on that in a second, it's going to be our most interesting piece here. Magnitude of R, well, that we always said was going to be 1. And then we have an angle between those two, sine of theta. that changes as we move around the term there. Now this is going to end up being the magnitude of dl, right? So this term goes to 1. And if we think about the angle here, this is also going to go to 1 because the dl anywhere along this curved arc is going to be a little tangent. So that's dl there, but r hat is pointing this direction. And so those are going to be at 90 degrees to one another the whole time around. dl now is a little piece of arc, and so this is going to be r2 times what I was calling d phi, which is our angle around the arc. And this means that for 3, we're going to have something very similar. The magnitude of this is simply going to be dl, which is going to be r1 times d phi. Okay, now let's compute these two segments. So we'll do 1 first. Let's add up the magnetic field that the outer arc produces. So that's going to be all the little pieces of the magnetic field. And we said that this is going to be out of the page. We already know that by our right-hand rule. So this is mu naught times I over 4 pi. dl crossed into r hat over r squared. Lots of constants here. So this is mu naught I over 4 pi. And we said that this term is going to be r2 d phi over r2 squared for that first segment. So our r2s are going to cancel, and that's a term that we can bring outside. And so what's left is mu naught I over 4 pi. We'll factor out our r2 down here. And we're going to integrate over our angle phi, which in this case is a semicircle, and so we're going to get a pi as our angle. And this is going to be 4 pi r2. Pi's cancel. And so we're left with a mu naught I over 4 r2 coming out of the page. Now, for what we were calling segment 3, well, the setup is exactly the same, and so the only difference is the direction, right? So now I can just jump right to the end here. This is going to be another mu naught I over 4 r1, and this is going into the page. So we have this piece that's going into the page, and this piece over here that's coming out of the page. And you could say, well, when I add the two together, right, 1 plus 3, which is going to be the larger component, all right, because I can make one of these terms negative and do the subtraction that way. And since r1 is a smaller number at 4.5 centimeters, this term is going to be bigger than this term. And so when I add these together, I can get a b for our total magnitude. It's going to be mu naught I. I can factor out all the common terms here. Mu naught I over 4. And a 1 over r1 minus a 1 over r2, because they are in opposite directions. And I know I can look up mu naught, and I know r1 and r2. And so when I plug all of these things in, I actually get a value 3.29 times 10 to the minus 6 Teslas. And that is going to be into the page. And we are done.